functions can't have variables in the denominator. Rational functions have denominators that contain variables, okay? So the parent graph that we will still talk about shifts and stretches and compressions and all that good stuff is 1 over x, and it looks like this. So one of the first things we have that you've had in the past with exponential graphs, log graphs, are asymptotes. But with rational functions, there are both vertical and horizontal. Like, I know we haven't reviewed it yet, but exponential functions have a horizontal asymptote, right? Log functions have this vertical asymptote. Rational functions have one, sometimes more of each. Okie doke? So, in your parent graph, your asymptotes are the x-axis, aka y equals 0, and the y-axis, aka x equals 0. And then when we shift, those will shift with the problem. So let's go back to, if the asymptote is y equals 0 and x equals 0, that means that really technically our x coordinate will never equal 0. So why can't, just looking at the parent graph, I think this is an obvious answer. I'm sorry about that mark on there. It kind of makes it look like an 11. It's just a 1 over x. Why can't x be 0? Nate? No, look at the function. From an algebraic perspective, why can't x be 0? Right, and undefined, exactly. F of 0 equals 1 over 0 is undefined. So that makes sense as to why we have an asymptote right here, and it kind of blocks off x being allowed to be 0. What's maybe a little bit tougher to wrap your head around is why can't y ever equal 0? Why will this function never equal 0? Aiden.
Because the only way for that equals 0 would be if the numerator changed, and it won't because it's not a variable.
Perfect. The only way for a fraction to equal 0 is if the numerator equals 0, right? 0 divided by anything is 0. And because it's a fixed number, a 1, it will never equal 0. Does that make sense? Okay. So there's our asymptotes. Our domain is from negative infinity up until but not including 0, and then a union with 0 up until infinity. Again, not including 0. So pretty much it's negative infinity to infinity, but just with the exception of 0. And the range, same thing. It's pretty much negative infinity to infinity, but because we skip over 0, we have to do that. Now, first of all, down here, a little notation. If you had to read this, how would you read that, Andrew? As
X goes to 0.
Okay. Yes, essentially. But in math, we say approaches. Okay, so as x approaches 0, this is a notation I don't think you've ever seen before. This is a little superscript that's a plus sign. That means as x is approaching 0 from the right, and then the next one is as x approaches 0 from the left. Because different things are happening. Here's an x-coordinate of 0, right on that y-axis. As we approach 0 from the right, where's this f of x headed? As we approach 0 on the graph from the right side, does everyone see how I'm coming at it from the right? Where's my y-coordinate headed? Infinity. As I approach the x-coordinate from the left-hand side, where is my f of x value headed? Say it into my good ear. Negative infinity. Good. So what we see here is what is, I always hate to use the word always unless I'm sure. What is always going to be true as we approach an asymptote, a vertical asymptote. 0, we all can agree, is a vertical asymptote. As I approach a vertical asymptote, your graph, because it can't be crossed, right? Vertical asymptotes cannot be crossed. Your graph will either shoot up towards infinity or negative infinity. So anytime you're approaching a vertical asymptote, your f of x will be approaching either infinity or negative infinity. Does that make sense? Okay. Obviously, visually, we can see what we just came up with. Let's pretend we didn't have a graph. And let's pretend we didn't know what this looked like. If x is approaching 0 from the right, give me a number that's slightly to the right of 0. Connor? 1. Okay, that's 1. Give me something, Connor, that's closer to 0 from the right. Half? Give me something even closer, please. A fourth? You're not making very strong leaps here. Give me something even closer, and don't tell me an eighth. 1/100th. I love it. What's that? What's 1 divided by 1/100th? What's 1 divided by 1/100th? 100. Let's really kill it. F of 1 over a million. What's 1 divided by 1/1,000,000th? 1,000,000. So numerically we can see as our x coordinate gets closer and closer and closer to 0 coming from the right, aka the positive side, our numbers are getting infinitely larger. Yes? And because we can get infinitely close to 0 from the right, we can make that 1 over 100 gazillion trillion. Then this would be the massive number, 100 gazillion trillion, which is not a number, but I like that number. You follow, right? So numerically, you can see as we approach 0 from the right, our values approach infinity. And likewise, if I came towards 0 from the left, f of -1 would be -1. F of -1/2 would be -2. As I'm getting closer and closer to 0 from the negative side of things, that number is approaching negative infinity. So you should be able to wrap your head around that from a numerical perspective too. Okay? And also the big takeaway is anytime you approach a vertical asymptote on your x coordinate, your y coordinates will approach one of the infinities. Okie doke. Now, on the other end of things, we're not approaching a vertical asymptote here, we're approaching the infinities. What happens as my x coordinate is approaching infinity? What's happening to my y coordinate? What's it getting closer and closer to? Mackenzie. 0. Now, we should also be able to wrap our head around that because f of 1 is 1. F of 100 is 1/100th. As my x coordinates are growing, f of 1,000,000 will be 1/1,000,000th. And so as my x coordinates are going towards infinity, my y coordinates are shrinking, right? 1 over a number that keeps growing and growing and growing is going to get to be a smaller and smaller fraction. And on the negative infinity side, as x approaches negative infinity, so we go infinitely to the left, my y-coordinate is approaching what, Mitch?
0 again.
0 again. Okie doke. Now this is considered end behavior. End behavior is any time your x-coordinate approaches infinity or negative infinity. It's just with polynomials, your end behavior always takes you towards one of the infinities, right? Where not always true with all functions. In fact, end behavior actually takes you towards horizontal asymptotes a lot of the times. Not always, a lot of the times. So 0 being our horizontal asymptote. Horizontal asymptotes are typically guiding behavior for the end behavior. They're guiding lines for the end behavior of a function. The same is true for this horizontal asymptote. That guides the end behavior going in the negative direction, only in that case. Does that make sense? And just like we said with our vertical asymptote, as this one approaches the vertical asymptote, we shoot off towards a negative infinity. And that's what happens. So that's just a general rule about asymptotes and what they do. I know you guys probably haven't seen this yet, but just for the record, vertical asymptotes, I'll write it, cannot be crossed. Horizontal asymptotes can be crossed. I don't know that you have seen an example of when a horizontal asymptote is crossed. Probably not yet, but we will definitely see a lot this year. Horizontal asymptotes really are there to guide end behavior, whereas vertical asymptotes are there to block out a value that can't be achieved. All right. So there's some rules you have to memorize regarding finding asymptotes. So pretend that your function, your rational function, is some p of x monomial or polynomial over some q of x monomial or polynomial. Okay? Your zeros of your denominator. If something is a 0 of your denominator, then it's a vertical, I should have put that in there. It is a vertical asymptote specifically. Your denominators allow you to see your vertical asymptotes. Unless, and that's what the second portion of it is, it's only a vertical asymptote as long as it's not also a 0 of the numerator. Because if it's a 0 of both the numerator and the denominator, then something unique happens. And we'll see that. So if I just look at this one, first of all, I'm going to find my domain, and I'm going to find any vertical asymptotes. Vertical asymptotes always come from your denominator. So the domain. What can't x be? X can be any real numbers except. John? 3? Oops. X can be any real numbers except x cannot equal 3 or negative 3. So there's our domain. Our vertical asymptotes, like I said, really come from the zeros of your denominator, which this one's obviously easier, but if you just want to factor it just to show yourself, the numbers that will zero out the denominator are negative 3 and positive 3. So your vertical asymptotes are x equals 3 and x equals negative 3. So this function actually has 2 vertical asymptotes, which again, I don't know if ever you've really studied anything like this. I'm thinking not. Here we go. X divided by x squared minus 9. Looks like this. So we have a vertical asymptote here and here. What's happening between the asymptotes and on the right-hand side and left-hand side of the asymptotes, we'll get to. But for now, just understanding what a two vertical asymptote situation looks like. On B, here's the deal. This function is one of those that's going to be that unique case. Negative 3 is a 0 of the denominator, yes, but it's also a 0 of the numerator, in which case it's not going to be a vertical asymptote. Because if you were simplifying, that would cancel. Negative 3 is not an asymptote. The only asymptote is x equals 3. But let's talk domain for a second. And you have to look at the original for this. The domain can be any real number except what? What is the value of g of 3? Bridget, what's g of 3 going to give you if you plug in 3? What over what?
6 over 0.
6 over 0. Is that okay?
No.
Of course not. So except x cannot equal 3. What about g of negative 3? If you plugged in negative 3, what would g of negative 3 give you, Sarah?
0 over 0.
Is that okay? No, so we can't be negative 3 either. So both of those numbers are still restricted from my domain, but they're not both vertical asymptotes. 3 is a vertical asymptote. When something cancels out, there's a hole in your graph at that 0. So x equals 3 is an asymptote. But at negative 3, you're not going to see an asymptote, you're going to see a hole. So when things simplify and cancel, you see a hole. I'll show you this. I will be honest with you, the calculator is not going to show you the hole. It does in a way. It's not going to be as glaringly obvious as I wish it would be. So here's your calculator. You will certainly only see one asymptote. There it is at 3. You certainly don't see an asymptote at negative 3. I'm going to zoom this in from negative 5 to 5 so that doesn't look like it disappears quite as soon. Sometimes your calculator shows you the hole, but you really have to zoom in a lot. So if I, and still sometimes it doesn't. If I zoom in over to negative 3, over in here, it's going to highlight that part of the graph for me. Where's my cursor? Yeah, it would be right around there, and it just really doesn't show it. The way I'll know it's there is if I do second trace and value, and I type in negative 3 to see what the coordinate is at negative 3, it will come up empty. There's nothing there. And if you look at your table, you'll just see an error at negative 3. You'll see things to both sides, no problem. But you'll see an error right at negative 3 because there is no point there. Because when we plugged in negative 3, we got 0 over 0. So there's no output for that. Do we follow? Okay. So if I was drawing this, and when we get to the point of drawing, you guys will put your asymptote at 3, and it did this. And then what you'll do at negative 3 that this doesn't do is you'll put a very obvious hole there. The calculator's graphics aren't good enough to show it. Mitch, are you with me? Yeah. Mitch This is important stuff, my friend. Any questions? Okay, and on the last one, the denominator is actually not factorable at all, so certainly nothing's going to cancel. What's our domain? X can be any real number except what? What are the exceptions here? What X value would make that denominator 0? If I do h of 3, I'll get something over 18. If I do h of negative 3, I'll get something over 18. That's fine. Right? Trick question because all real numbers. There are no exceptions. And if there are no blocked out X values, then there's definitely no asymptotes, no vertical ones. Okay, so no vertical asymptotes. Just for fun, this looks like, oh shoot, I'm zoomed in from the last problem where I left off. Zoom 6 will put me back negative 10 to 10. That's kind of funny. Window. I'm going to zoom in negative 2 to 2. So I was not as zoomed out so I could see a little bit more what fluctuations were happening. And we will get to a point where you'll have to and you'll be able to come up with that on your own. We're not there yet, but okay. To the back. Horizontal asymptotes. This is something brand new to you, how to find these, okay? So there's 3 rules, and the rules for where the horizontal asymptotes are is dependent upon the degree of the numerator as it compares with the degree of the denominator. So you need to compare the degree of your numerator to degree of denominator. And there are 3 scenarios. If the numerator's degree is smaller and the denominator's degree is the bigger of the 2, then the horizontal asymptote is at y equals 0. That is our parent graph situation. Because think about your parent graph. 1 over x. What's the degree of the numerator? 0. What's the degree of the denominator? 1. So it's small over big, right? And when that is the case, you have an asymptote right on the x-axis at y equals 0. The second scenario is bigger over smaller, in which case horizontal asymptote does not exist. Did we have a bigger over smaller on the other side? No, they were all small over big. They were all small over big on the front side, right? 1 over 2, 1 over 2, 1 over 2. So all of those that we looked at, including that last one, by the way, and this is really the first time you're seeing it, this does have a horizontal asymptote at 0. It crosses it. You can cross horizontal asymptotes. But that horizontal asymptote of 0 guides end behavior. So as we go towards positive infinity, it approaches that horizontal asymptote of 0. And as we go towards negative infinity, it approaches that horizontal asymptote of 0 as well. Horizontal asymptotes guide end behavior. They can be crossed. And then the last example is the same over same. So for example, if something had a degree of 2 in the numerator, and it also had a degree of 2 in the denominator, your horizontal is y equals, in this case, 5/3. This one has a horizontal asymptote of 5/3. Where obviously is that coming from? 5/3 is coming from the coefficients. Y equals leading coefficient over leading coefficient. So you have to remember these rules. Small over big, big over small, same over same. I would argue you already know the small over big because it's the parent graph. In A, which category is this? Small over big, big over small, same over same. What's the degree of the numerator, John?
Of the what, sorry?
The degree of the numerator in A. 1. And the degree of the denominator, Morgan? 2. So 1/2 is small over big. So there's your horizontal asymptote. Look at B. What rule does that fall into? Go ahead, Marissa. Same over same. So your asymptote is what?
4/2.
Say it again.
4/2.
Which is 2. And the third one, go ahead and do that. What's your asymptote there, Olivia? Does not exist. Big over small does not exist. So the end behavior in these two cases approach 0. The end behavior in this case approaches 2. And the end behavior in this case doesn't approach a number, probably approaches one of the infinities. So I graphed all 3 of these. Here's the first one. Okay, we said that the horizontal asymptote was at y equals 0. Can you see it? How when we go towards infinity, we get towards 0. When we go towards negative infinity, we get towards 0. We cross it. Well, that's just a reality. You can cross those. Something funky happens here. We'll have a way of figuring out the rest of the look at that graph soon. But we're just starting with asymptotes today. On the second one, turn that one off, turn that one on. Mind you, my y-axis is only going from -2 to 2 right now. So do you see how my end behavior is kind of balancing off at 2 on both sides? That's because of my horizontal asymptote. Something funky is happening in the middle. We'll get there. But for now, you see the horizontal asymptote showing its face. And the last one, turn that off, turn that on. This one just kind of looks like, almost like a cubic graph, doesn't it? Like almost like, it's not, but it almost looks like it. But my point is, its end behavior is not flattening out on a horizontal asymptote line, right? It's going towards the infinities. Do me a favor. Let's do long division on this. Let's take 4x cubed and actually divide it by 2x squared plus 1. So I'm going to fill with 0x squared plus 0x plus 0. See what happens. So 2x squared times what gives me 4x cubed? Children, 2x squared times what gives me 4x cubed? Yeah, you guys don't have to raise your hand. And then when I multiply this times this, Joe, what do I write down underneath?
Plus 2x.
Good. Now that 2x isn't lined up right, is it? I have to move it over. Subtraction, subtraction. My 4x cubes will cancel. I'll have a 0 x squared minus a 2x. And I repeat. 2x squared times what gives me 0x squared? What? 0. So I get 0x squared plus 0. Do my subtraction. I'll have negative 2x minus 0, which is just that. And then I repeat. 2x squared times what is negative 2x? I'm done, right? Because I can't use negative exponents. So this is just my remainder. And I'll tell you what. There are no horizontal asymptotes on this one. We also can ignore the remainder. You know what our asymptote is? Y equals 2x. If I go back to that graph, and it looked like that. I zoomed out a little bit. I made it negative 10 and 10. There is a little fluctuation happening there. If I also graph the line 2x, it's an asymptote to the end behavior of that. Do you see that? If I zoom in, maybe change my window, negative 5 to 5 and negative 5 to 5, you'll see a little more of the, that's the 2x line. And there's my weird polynomial line that came up and looked like it sort of wiggled. But that line of 2x is what this is getting closer and closer to. And the line of 2x up top is what it gets closer and closer to as we go towards infinity. It diverges from it a bit in the middle, who cares? But end behavior-wise, it gets closer and closer to 2x. Meaning, if we were to plug 100 into this, that value, h of 100, would be very close to 200. Right? The further towards infinity we get, the closer this value, h of 1,000, will be very, very close to 2,000. Even closer than the 100 values were. Because as you go towards infinity, your function gets closer and closer to your, this is called the slant asymptote. Nothing fancy about that word, right? It is what it is. It's not a horizontal asymptote. It's a linear one usually. They don't even always have to be linear either, by the way. You can have, believe it or not, like a quadratic asymptote. You would just show your asymptote with a dotted line, and you'd show your function with a solid line that gets closer and closer to that structure on the end behavior. Okay, so that's a big step from what you knew before to what you should know now if you didn't sleep through my class.
Sorry.
It's okay. You weren't the only one with your eyes closed at moments. Mental toughness, kids. Fight through it. Try to psych yourself out and make yourself think this is the most exciting thing in the world.